Okay, hi everyone. Thanks to the organizer for organizing this great conference, despite the conditions. So yeah, this talks about EthBadgerMPC and Ratel, which is a sort of kind of programming language. As you can see in the corner, bottom right corner, this is work in progress. This is very important. So we're in the midst of working on this. So many things are not yet figured out, but I still wanted to present what we have and also open, it's an invitation for people who have thoughts and can provide useful input. That will be a good opportunity because the thing is really under development. This is work I'm doing with Andrew Miller at UIUC and his Decentralized Systems Lab group with other grad students as well. So a brief outline, I just want to start just providing background, motivation, and challenges. Then I'll dive into what this Ratel language is about conceptually, and then the current implementation. After that, we'll present, there's this thing which I call the EthBadgerMPC framework and architecture. So I'll cover this. And if time allows, I want to maybe show a detailed view of the orchestration mechanism in a concrete example, and then future work. So I will dive into what's the background very briefly of this. This is based on EthBadgerMPC and asynchronous work that Andrew presented yesterday. So I don't want to repeat things, and Andrew did a much better job at explaining the details. So this is more like, the goal here is to present more kind of the engineering side and what we're currently trying to develop. But basically the setup is a MPC as a service, where you have clients that submit inputs that are meant to be kept secret. And it's using Ethereum as a kind of privacy layer. And then the MPC, there's a kind of coordination mechanism in place such that the MPC server can consume these inputs and operate on them on the secret shares. Okay, so I keep going to. So now what's the motivation behind doing this work? It's like one of the motivations, like orchestrating MPC, is actually turns out to be important. There's a kind of win-win situation for both sides, like here. So the MPC network, like as a service, can benefit from some kind of coordination mechanism, and Ethereum provides a kind of decentralized way to do that. But then on the other hand, there's Ethereum that benefits from having this kind of privacy layer that Andrew spoke about in his talk yesterday. Then another motivation is like providing a programming abstraction for application developers. So you'll see that later in a few slides that one of the ideas that we would like to provide a framework that develop, just like right now with Ethereum contracts, you focus on writing a contract and you deploy it with some, let's say, Web3 tools to the chain, and that's it. That's mostly your focus. So we would like to kind of provide a framework like that where you write MPC programs within that framework, and they get deployed to the MPC network, and that's pretty much it. Then there's a big chunk of the work I've done so far that I'm going to be presenting. It's providing a kind of useful development environment and tool chain to iterate rapidly. Because I should mention that the context here, we're in a research context, so we're mostly concerned with prototyping and proving results and benchmarking and so on. However, there's still like a direction where this can move towards like more substantial implementations, like a testnet or something like that. So this is one of the motivation as well. And then providing reproducible builds, reproducible benchmarks and results. This is very important for research, and also for, I think, anyone who does software, you want to be able to reproduce bugs, results, whether it's good or bad. Reproducing something is very important. So that's another of the motivation for this framework. I'd like to briefly touch on like challenges for MPC in dynamic environment. I just came across this like a few days ago. It's a paper called Management Framework for Secure Multi-Party Computation in Dynamic Environments. And they mentioned like these, okay, the sort of like context in which they discuss this is like, let's say, a smart city. And this is interesting because you have all this data coming from sensors and so on, and then you want to preserve the privacy of the users of the source data, but you want to be able to maybe get some interesting statistics, and you don't care about the source data itself, but you care about the statistics being like public resources, if you want. So that's their context in which they discuss this, and MPC is a good fit. It's a good solution for that problem. However, they mention like many challenges into like, if you really want to run this for a real application, how do you manage the secure multi-party computation like network? So just briefly going over some of the points I mentioned, it's like the setup phase, like establishing the secure channels, discovering nodes, and how do you make the MPC network agree on which program to compute at a given point in time? So this is where actually what we're doing, our work actually shares a lot of resemblance with this work. However, they're using a kind of gateway node. So in which and then you can rotate that gateway node. But I think like using Ethereum provides many advantages, and plus it provides many things that you cannot get with just a normal like server that coordinates these operations. So it's just something to keep in mind. I wanted to also mention like some of the kind of motivation behind this work as I'm doing that is I keep in mind like when you develop within like a research academic context, it's not like working in a startup or in a company. There's like many kind of trade-offs that people have to do. So meanwhile, developing this framework, we're keeping this in mind because one of the key ideas is to be able that for grad students and people who do research work, they want to quickly write a EthBadger MPC application and maybe deploy it to benchmark and so on. But it needs to be fast, but at the same time, you want to kind of get some of the advantages you get from kind of industry-like software where you can have like a nice tool chain where it's easy to get set up. And also like grad students, like they come in and out. So like next year, if someone new comes in, do we have some documentation? Can they reuse what someone did in his master thesis, say? So that's one of the also things that is motivating the work I'm presenting right now. Okay, so Ratel. So just what is this about really? So how do we define MPC programs in Vyper? Vyper, for those who don't know, is like a smart contract language for Ethereum, like Solidity. It's like resembles Python a lot. And we use that because it was kind of easier to work with to sort of experiment. So I'd like to walk through this kind of diagram that you see right now. So the way it works is like a developer would write a Ratel contract, which consists of Vyper code, like nothing changed there, but then would add like function definitions for MPC programs. And the compiler for this Ratel contract, what it would do, it would like produce the normal EVM bytecode that is deployed to Ethereum, but then it would produce also like MPC code that would be deployed to an EthBadger MPC network. And you can see like the way it works, there's a bit like, now this is the vision which I'm presenting here. So this is like really what we're working on right now. But ideally would be that whatever is deployed to the MPC network is sufficient for the whole thing to function. And then there's like the coordination mechanism or like sort of like programmed baked into what is deployed to the MPC network. And then the secret data coming from the, so the way it works is like users would input their secret data to or kind of encoded data to the Ethereum network to a contract. And then EthBadger MPC like consumes the secret data, performs a computation, and then outputs the result of the computation to the contract, which whoever wants to consume can consume. So a very brief example of a kind of like, it's somewhat like pseudo code. It's almost identical to what we have in our implementation, but very simple, like if you would want to do a random permutation of shares of elements. So the way it would work here, like using this decorator MPC, defining like which pre-processing elements are required for the execution of that program. And then just simply call permute and then open the shares and return the result of the computation. So maybe I thought because this is not something Andrew talked about, like how do we do that right now? How do we compile these Ratel programs? So the way it works, I just kind of use it's very primitive right now, but still the way it works is like we use the Vyper as a pre-parser that it parses the contract code with to make it into valid like Python code, because a Vyper code looks like Python, but it's not valid Python code. So I'm using that. So the whole contract, both MPC functions and Vyper code is compiled well, not compiled, but it's transformed into, it uses the Python tokenized standard library. So it's transformed into valid Python code. Then using the Python abstract syntax tree library, it allows to split the code into two parts. So the pure Vyper code and the MPC part. Then once this is split, the original Vyper part that has been Pythonized is unparsed so that it can be like compiled using the Vyper compiler. So it's just like a trick like that. And this simpler doing that allowed us not to have to kind of like modify the Vyper code. So the framework, so I'd like to show the stack here a bit. So on the right-hand side, you can see what is a EthBadger MPC server. So there's this bottom layer, like on EthBadger MPC code layer, which actually, now this is for presenting the thing, but this is where actually most of the code is. But this is Andrew's group wrote that last year. This is where you have all the toolkit to do the fancy mathematical operations that MPC relies on, but we're building on top of that. So the orange square is where it's interesting for the purpose of this talk. So what does this do? So there's this offline pre-processing that is continuously running, and it writes the pre-processing elements to a level DB database that is local to each server. Then there's an HTTP server that is responsible to handle client requests who are asking for input masks. Then there's this MPC program runner, and this little black box here is the actual MPC program that I showed earlier in this pseudo snippet code. This is where it gets like injected right now. We're just like very like, it's kind of brutal, very raw. We just inject it into the MPC code here. And then there's this layer of Python code that coordinates, that uses web3.py to make calls to the contract and to coordinate the operations. Basically like, okay, is it time to start the MPC program? And when it's time to start it, okay, the computation kicks in. This is a snippet of code just to show, I showed earlier like how the parsing and compilation of the Ratel contract works, the splitting into two parts of Vyper code and MPC code. So this is actual real code, in the sense that that's the code that is executed when we run the framework. So there's this compile Ratel contract, and then we get the Vyper output and NPC output. And the reason why I wanted to show that is like you can see here, we just like get the normal contract object to interact with Ethereum, like as you would normally do. And now this is why I'm presenting this, by the way, like this is like very like, rudimentary how we do that. We just have the pure source code of the MPC program definition, which we just pass to the Python built-in exec, just so it can be accessible within the code. But the work we're doing would be like where we would refine that, like, to various degrees as we proceed, as we progress. I wanted to talk, so a lot of the work that we've been doing in the past months is more about tooling, so to lay the foundation for now what I would call more like kind of experimental and research oriented work. But basically, like, there's lots of things, like, so we use Docker and Docker Compose for everything. And when you develop an application within this framework, you get these, each logical component is its own container. So and then you can run a very kind of tiny simulation network locally to just check that everything works. And this simulation network contains the development Ethereum blockchain with Ganache, and a little client to kind of mock a client, and MPC servers, like 4 of them, say, that interact. But each one is its own container. So the advantage of this is that if we want to move to a cloud infrastructure or a kind of dev network, or it's more, or logical components that are expected to be isolated in a real world scenario, the ground's already set for that type of work. And also working towards reproducible research, this is very useful. I don't know how I am on the time right now. How much time do I have left, Surya?
You have approximately 30 seconds.
Oh, really? Okay. Well, I invite you. We have a README where it's like there's sequence diagrams of showing how the orchestration works between Ethereum and an MPC network, and how clients interact with Ethereum and the MPC network for this kind of like, this is based on asynchronous here, and how the execution works. And so maybe I quickly go to future work, future directions. So well, I don't know maybe I should open to questions if I already ran out of time.
Maybe just share this last slide on Slack, and we don't have time for questions at the moment, so we will.
Yeah, just briefly, it was really a challenge because there's lots of moving parts here, moving components that are really being worked right now on. And so to pack this into a 10, 15 minute talk was really a challenge. But everything is on GitHub. And so if people have questions, everything is open source. So you're all welcome to ask questions via these channels. So thank you, everyone. And here are some at the end, are some like current software artifacts we have. So thanks.
Yep. Thank you, Sylvain.